We begin by observing nature. A protein doesn't stay on a long floppy chain of amino acids. It folds up into a very specific three-dimensional structure. It's like if someone handed you a shoelace and it tied itself. A particular sequence of amino acids in the chain determines the structure of the protein, and the structure, in turn, determines the function. All life on Earth has proteins made from the same 20 amino acid building blocks. All life shares a common ancestor and a common genetic code, in which DNA codons are interpreted as these particular 20 canonical amino acids. Now, about half of these amino acids are what we call hydrophilic. They like to interact with water. The other half are what we call hydrophobic. They like to bury themselves away from water, just like oil separating out from water. And it's this burial that drives a protein to fold. Chemists can synthesize thousands of different amino acids and amino acid-like building blocks that don't exist in nature, and can use them to make synthetic molecules. We might look around at nature and see that there are birds, and there are bats, and there are insects, and they have wings and they can fly. And the simplest thing you might try to do is to emulate that. We've taken the principles of aerodynamics, and we've used them to make airplanes, but we've gone beyond that, and we've made helicopters, we've made rockets, and we've thought about new ways that things can fly. The real test of whether you really understand the principles that underlie a physical phenomenon is when you can take those principles and reason out a way of applying them to accomplish something that nature has never accomplished. And this is what we want to do with molecular engineering. We want to be inspired by the molecules that exist out there in the world, but we also want to go beyond them. We ask ourselves, can we build a molecule made of synthetic building blocks that don't exist in nature, which folds up into a three-dimensional structure beyond the structures that natural proteins can fold into, and which can perform some function beyond the functions that are accessible to natural proteins? If we can do that, then that's the ultimate proof that we understand how proteins fold and function. Before we can do this, we need to make the tools that allow us to design these molecules. And our tools are algorithms. But there are big challenges. One of the challenges is that as the design problem gets large, meaning that as we're either trying to design large molecules made from many building blocks, or we're trying to design molecules made from many different choices of what the building blocks could be, we hit a ceiling of tractability where our algorithms no longer work. So how do we search through such a vast ocean of possibilities, particularly when only a trivially small fraction of all the possible sequences fold into anything at all? Our algorithms treat the problem as a landscape to be searched, with mountains representing bad sequences and valleys representing good sequences. But it's like we're nearsighted. We can only see one point of the landscape at a time. We search, climbing the hills and rolling down into the valleys to try to find the very lowest point, the best sequence. Our algorithms work pretty well for fairly large landscapes. But if we go from having 20 amino acids to having thousands, the landscape becomes astronomically large. The number of possible sequences dwarfs not just the number of grains of sand on Earth, but the number of grains of sand in the entire universe. And so we're always trying to make the algorithms not just better, but cleverer, so that they can search larger and larger landscapes. These tools, and the molecules that we make with them, can have practical applications as well. If we can design molecules that fold into rigid structures, then we can design drugs. Drugs have to be shaped to bind to target proteins, either in humans or in bacteria or viruses, just like a key has to be shaped to fit a lock. Most of the drugs we currently use are like luggage keys. They're small, which means they don't recognize their lock very well. And when they fit in other locks, they cause side effects. We want to make big molecules, like house keys, that are perfectly shaped to fit one lock only. With antibiotic-resistant bacteria on the rise, we urgently need ways of designing new drugs. Beyond testing our understanding of protein folding, beyond making new drugs, we designed for another reason: pure curiosity. Why did nature use these particular 20 amino acids? What else could it have used? If we were to find life beneath the ice of one of Jupiter's moons, like Europa, what might the biomolecules of that life look like? What would they be made of? They almost certainly wouldn't be made of the same 20 amino acids that we use. This is why we set out to go beyond the 20 and to develop the tools to design with exotic chemical building blocks. We knew that if we could do that, it would be like magic.